All right, good morning again, everyone. Today we'll talk about integration by parts, which is another technique of integration that you can add to your repertoire, which will help us handle some more complicated integrals, particularly either that are either a quotient or a product of complicated functions, wherein U substitution won't work. I see somebody sent in a question, so I'll go to that later. Okay. Was the question deleted? I can answer that later. I remember somebody sent that. But anyway, so that's integration by parts. But before we go ahead, just let me know if you have some other questions about improper integrals. Yeah, I can probably go over a couple of examples for that. But we were told by Dr. Almas that he started the IBP last week, but I guess you guys are preparing and are focused on the preparations for test number 2, so you probably didn't have too much time um, working on problems with IBP, or you simply did not focus on it yet because you are preoccupied with the exam preparations. So that's why I wanna answer as many IBP problems as possible. And Kingsley, yes, this worksheet is already uploaded in my website. So it's on the blank worksheet part, worksheet number 8. But basically, worksheet number 8 contains some problems from the textbook again. But I'll be happy to answer some of your questions if you encountered more difficult problems in the quizzes or the homeworks, right? But before we begin, let's have a quick recap of what integration by parts is. As I mentioned earlier, IBP is a usual trick we use whenever integrating a product. So, so this is commonly used for integrals involving complicated products. And it says that if you have such an integral, so you'll have a u dv, you want to integrate u times dv, then the formula says it is equal to u times v minus integral of v du. Let's call this formula 1. This is basically what you need to remember for IBP. So u dv equals uv minus v du. And the trick here is choose a u and a dv from the original integral. So imagine your integrand comprising of a product. Then you can choose or take one of those factors as your u and the other factor as your dv. But always remember that when you're choosing something as your dv, this should include the dx. And then once you have picked your u and dv, we need to calculate du and v in order for us to be able to use formula number 1. So basically, the crux or the critical juncture in applying the integration by parts is in choosing what should be the function u and what would be the differential dv, because you cannot, for some problems, you cannot simply interchange the choice, because an improper choice for u and dv might give you a more complicated integral in the end. Because remember, even if you were able to apply the formula for IBP, you'll still come up with this, which still has the integral, but this time the integral v du. So your goal here is to to choose u and dv, so that the integral of v du is much easier to evaluate than the integral of u dv. Right? So this is a very powerful tool. So if there are some math majors in the class, you'll encounter this in your more advanced classes, even the theoretical classes. So I hope you guys will pay attention. And as I've mentioned, it's crucial to choose the right u and the correct dv. So to guide you with the choice of u, we have this mnemonic. You can remember the mnemonic ILATE. This mnemonic gives us the order of precedence or the hierarchy for choosing the function u. If your integrand involves an inverse trig function, and that's what the I stands for, that would be your first choice for the u. And it should be followed by logarithms. A is algebraic. T is for trigonometric. And E is for exponential. So whichever comes first in the list, that would be that usually is the better choice for you. And then whatever remains would be your choice for the DV. So this is a good good mnemonic to remember to give you the candidate for you. Another choice is that usual choice for you would be the one that has a derivative that goes to 0. So I mean, another option is to choose u so that has higher order derivative that decays to 0. And I'll show you later why I wrote that because you will see that whenever you compute du, it's a big advantage if later in time the du will become equal to 0. So I guess it's, again, much easier to understand all of these things if we go with some examples. So just remember formula number 1, that's all I'll use, and then plus the mnemonic isolate for the choice of u and dv. All right. So let me go over worksheet number 8, some of the problems there. Okay, so let's try some of these. So you can go ahead and browse worksheet number 8 and then let me know if there is an interesting one or something that catches your attention. Let's try problem 4 while you are browsing. So problem 4, integral of x ln x dx. Now I see that this integral involves a product of x and ln x. If you are confronted with such a case, then well, here u substitution will not work, right? So the next best option for products like these would be integration by parts. So you know that u substitution will not work because our candidate for u would be ln x, du will be 1 over x, and we don't have a 1 over x. So here I'll use IBP. So I will take u to be equal to, remember, isolate logarithms. Maybe I should write that down here for a while. So I have a logarithm over here, and I have x, which is algebraic. L precedes a in the mnemonic. So my choice for u would be the logarithm ln x. Okay. And then whatever remains, that would be our dv. So here our dv is x dx. So once you have your choice for u and dv, we need to compute du and compute v. Well, du would be what? The derivative of ln x. So that's going to be 1 over x dx. And then v would be the integral of x dx. So to compute to compute for v, what you need to do is to integrate both sides, right? So we get v, or at least get one antiderivative. So this is x squared over 2. You don't need to put a plus c there because plus c will just be gone once we do the integration. So yeah, just choose c to be equal to 0 in your choice for v. And then applying formula 1, the original integral becomes uv. So that's x squared over 2 ln x minus integral of v du. So that's going to be x squared over 2 times du, which is 1 over x dx. All right. And then I'm hoping that this integral here is easy to evaluate, or much easier to evaluate than the original one. And I guess it is after we do the simplification. So let's just copy the first term over. Then simplify this. I'll have what? I'll have x dx times 1/2 outside. So this will be x squared over 2 ln x minus 1 over 2 times x squared over 2 plus the arbitrary constant c. So essentially we'll have x squared over 2 ln x minus x squared over 4 plus c. All right. So that's the basic idea. So it's the crucial thing again here is to choose u and dv properly, because that will dictate whether you'll have an easy time integrating. And you see here that I chose u to be lnx because of the acronym isolate. Or actually another thing is that you can choose u to be the one that is easily differentiable and dv to be the easy to integrate, right? So you see the difficulty if you take dv to be ln x dx, then you need to integrate ln x dx, and the integral is not pretty, right? Because the integral of ln x is another complicated integral that was actually computed using IBP. Okay, so any questions with this? Our first example? None? I guess the acronym isolate really helps a lot in determining what would be the choice for U and DV. So have you guys had a chance to look at the worksheet? Anything that caught your interest? Mm, one thing about integration by parts is that it can be it can be used repetitively. I mean, as long as you cannot integrate that integral of VDU, you can repeat the process over and over again. But of course, you don't want to do it a lot of times, but sometimes you don't have a choice. So let me try problem number 6. So here we have x squared e to the negative x dx. Again, you can try u substitution here. It won't work. So the next best choice, since you see that the integrand is a product, we try integration by parts. And in integration by parts, again, you need to determine what would be your u and dv. Okay. And then you can rely on the acronym isolate. So what are the involved functions here? We have x squared, which is algebraic. And then we have e to the negative x, which is exponential. So a precedes e. So I will choose u to be the algebraic function and dv to be the exponential function together with the differential dx. All right. And so if we do after the choice, you compute for du and we compute for v. Du would be 2x dx, and v would be, you can use u substitution here, but essentially you'll get negative e to the minus x, right? That's the antiderivative, or that's an antiderivative of e to the negative x. And then use formula number 1. The original integral is equal to uv. So this is going to be x squared times negative e to the minus x minus integral of v du. So v is negative e to the minus x, du is 2x dx, right? Let me just rewrite this as a negative x squared e to the minus x plus 2 integral of x e to the minus x dx. Okay, good so far? Now I have a bit of a problem here. Look at the integral here at this point, the integral that we have. This guy. This guy is still a product. And then no matter what I try for a u substitution here will not work. But I realize, oh, this is another product. So that means I can use u substitution. I can use IBP one more time. So, and then what are the functions involved here? I have an algebraic function x. I have an exponential function e to the minus x. Using isolate, I will take u to be the algebraic function again, which will be x. And then I'll use dv again. For dv again, e to the minus x dx. Then I'll compute for du. Du will be dx. And then v would be negative e to the minus x dx as before, right? And so here, I'll have negative x squared e to the minus x plus 2 times. Remember, I'm using integration by parts on this integral. So this comes out as uv, the new u and v. So that's u times v minus integral of v du. So minus e to the minus x. Oops, there's no dx here. So that's a v du. And the remaining integral here is easy to evaluate. It's just the integral of negative e to the minus x. So you can rewrite it as minus x squared e to the minus x minus 2x e to the minus x plus integral of e to the minus x dx. There's a 2 in front. Okay. And then I can integrate the remaining integral here easily. You can let u to be equal to negative x, then du is negative dx. So that just comes at the cost of a negative sign. So this is negative 2 e to the minus x plus the arbitrary constant c. Okay. So this second example teaches us that integration by parts might be required to be applied more than once in a particular problem. So you just need to be careful about with the grouping symbols, because the complication here, if you remember Formula 1, you have a negative sign in front. So if it turns out if you will be using integration by parts a couple of times, then make sure to track that negative sign all throughout your solution. Yeah, and imagine it's just your right person. Imagine this is just x squared e to the minus x. Well, perhaps you can play with the one that has a larger exponent. So let's see. Okay, but before I proceed, any questions so far here? None. But you see, however long the solution is, I mean, it's just being consistent about the choice of the u and v and with the grouping symbols. So I'll add this example. I'll use a bullet here because it's not part of the worksheet that I have prepared. But say you have the integral of x to the fourth, and then you have sine x dx, right? Again, any u substitution here won't work. But IBP will, because we have a product here. We have an algebraic function x to the fourth and a sine x dx. But imagine what will happen if you will extrapolate from the previous problem that we had. From the previous problem, we have an x squared e to the minus x. But here we have x to the fourth sine x dx. So here I'm expecting that we will use IBP 4 times. And it would be a lot to write the solution in this manner. Imagine how long will it be. Sometimes I use tabular IBP when I know that it will entail several iterations of the method for me to finally get the answer. So, and this is particularly useful whenever one of the factors involved will have a higher order derivative that goes to 0. If you look at x to the fourth, what are the derivatives of x to the fourth? It's going to be 4x cubed, then 12x squared, then 24x, and then 24. The derivative of 24 is 0. So if I will keep on choosing u to be x to the fourth, right, and all of its derivatives, then eventually du's will be equal to 0. And I like the du's to be eventually equal to 0 because remember in the formula, in formula number 1, du appears over here. So when at some point in our solution, we are keep using IBP, but at some point when du is equal to 0, then the integral will be gone. So that's why I also want the u to be chosen so that will be chosen to be a function that will eventually will have a derivative equal to 0, right? And perhaps tabular IBP will show you why it is why that happens, right? But have you guys seen the tabular IBP in the lecture? Because from experience, I don't think they are presenting that form of a solution in the lecture, or some lecturers don't show that solution. How about you guys? Have you seen it? Okay, so yeah, I'll show it to you. So this is something that is again advantageous if you have one of the factors will have a higher order derivative that will go to zero, right? So again, I'll choose u to be x to the fourth, and then dv to be sine x dx, right? So I'll just omit the dx here, but remember, the column for dv all comes with the dx, right? And then I will keep on choosing u to be the one coming from x to the fourth. So basically, what do we do with the u's? We differentiate the u's, right? So basically here I'll have 4x cubed. If after doing another round of IBP, I will have a du, which is 12x squared. Another round of IBP will give me 24x. Another round will give me 24. Another round will give me 0. But the nice thing about this is after I get derivative 0, then everything here will be 0, right? And then now we go to the column for dv. Remember, how do we compute v from the dv? We integrate, right? So we need to integrate sine x. So what's the integral of sine x? It's negative cosine x, right? And then integral of negative cosine x is negative sine x. And then integral of negative sine x is cosine x. And then derivative integral of cosine x is sine x. And then after that, we'll have integral of sine x is negative cosine x. And then after negative cosine x, we'll have negative sine x, and so on, right? Okay, but I will stop there and you will see later why. Remember, the formula is uv minus integral of v du. So essentially what will happen here is that I'll have u and v. This would be my first uv, all right? And then the next uv will be this guy, or this product. Next uv will be this. Next uv will be this. Next uv will be that. Next uv will be this, the product. But I know that I can stop here because from here on, I'll have a 0 times whatever that function is. So that will be gone, right? So that's why I usually want du to be u to be something that will have a 0 higher order derivative, okay? So I'll stop there. That's why I knew I should stop the table here. And then remember, the formula has a negative sign. So that means there should be some alternating of the signs here. So basically, you do plus here, negative here, plus here, negative here, plus, minus, plus, and so on. So, okay, now we're ready to write the final product. So this integral over here, sorry, by repetitive IBP, which I arrange in a table like this, will be equal to the first diagonal product. So this guy, that's negative x to the fourth cosine x, right? And the next product will be this plus 4x cubed sine x, and then plus 12x squared cosine x, and then minus 24x sine x, then minus 24 cosine x, and then plus 0. I'll just affix the arbitrary constant c over here. And so that's your final answer. And this is also what you'll get if you do integration by parts, I think 4 times. So yeah. This is extremely helpful so that you don't have to write that long solution every time. Okay, just don't forget, you make a table for u by differentiating the previous entry, and then for the column for dv, you integrate the previous entry, and then you do the cross product or the diagonal product. But don't forget to also include alternating sign because formula 1 has uv minus the integral of v du. All right. Do you find this easier than you doing the IBP or the the paragraph form, what I call the paragraph form of the IBP, which is what we did for the previous example. Okay, guys, you're too quiet now. Any question? Hello, guys. Are you still there? Are you again trying to digest this? Okay, yeah, Arsalan, it usually takes um, couple of exercises before you get used to it. So, but I hope you see the process, the basic process. Yeah, let's try another one. Have you seen some good example from the exercises? Let's see. Let's try. We already did an ln. Perhaps let's do problem 20. Integral of sine root of x dx. So be careful here. The integrand is sine root x dx. This is not a product. This simply means that inside the sine is the root of x, right? So here we don't have any other choice but to take u to be equal to sine root x, and then dv to be chosen as dx, right? Again, the reason is I only have one factor here, and I will not choose dv to be equal to sine root x, because to get v, I need to integrate that, and we are having difficulties integrating sine of root x, right? So that's why I have root x over here, and then du will be a cosine of root x, then chain rule applies, 1 over 2 root x dx. And then here I'll have v is equal to x, okay? Then I'll apply formula number 1. It's uv, so it's x sine of root x. And now I am praying that the integral of v du is much easier to solve than the root of, than the original one, right? So here we'll have minus the integral of v du. So that's x over 2 root x, or maybe I should write it as as v times integral of, sorry, u times dv. So u times dv okay. And now what do we have here? We'll have x sine root x minus, I can put the 1/2 outside, and then I'll have root x times cosine root x dx. Okay, guys? Now, I think here we need another IVP because we ended up with another complicated integral over here, okay? And u substitution, can we do u substitution here? I don't think we can use u substitution. So I'll try IBP again. Remember for IBP, so here IBP again. And we'll choose islate, or we'll use the mnemonic islate, right? So what we have here, we have an algebraic function, root x, and a trigonometric function, cosine of root of x. So basically here, yeah. So here, I'm thinking, should I use an what's that, Herson? Isn't the square text a negative square root? What do you mean, Herson? In which part here? I mean here, I apply the chain rule. So I took the 1/2 out over there, and there's a negative sign over there. I'm thinking you meant here when I took the when I applied the chain rule. So it would be 1/2 x to the negative 1/2. That's why I have a square root of x in the denominator. Yeah, it would be 1 over square root of x. So basically here, but I have an x in front. Remember, it's the integral of v du. So I have an x here, then I have a root x here. So when I simplify x over root x, I have root x in the numerator. Okay, yeah. So, okay, so let's try IBP again, because I don't think use substitution will work here. I'm thinking now there is an easier solution here, but anyway, let me stick to this and let's see if we can solve it using this. So I'll again use u to be equal to cosine root x, and then dv to be equal to root x dx. The reason why I cannot use isolate here, though I have an algebraic against a trigonometric function, is that the trigonometric function is a bit complicated. You have cosine of root x, and I cannot integrate cosine of root x, so I cannot use it as a dv. So this is one example where in the isolate mnemonic I think doesn't work or will not give us a good substitution. But here, let's see. Hopefully this gives us a nice expression. So here du will be again 1 over this will give me again a negative sign, root x. And then I'll have 2 root x in the denominator again, right? I apply the chain rule. And then here v would be, well, this is x to the 1/2 dx. I integrate, I'll get x to the 3/2 times 2/3. Okay. So now, this is now getting complicated. Let's do this carefully. So I'll copy the uv from above, minus 1/2, and a grouping symbol here. We used IBP again, so we'll have uv. So that's cosine root x times 2/3 x to the 3/2 minus integral of the new v du, which will be 2/3 x to the 3/2 times negative sign root x over 2 root x dx. Okay, I hope you guys are following. I know this is now getting complicated. All right, so let's simplify this. I'll have x sine root x, and then I'll have minus 1/3 x to the 3/2 cosine root x plus 1/3, or there it should be a minus. Why? Because I have a minus here. I'll take that out with a minus there. So that's going to be positive, but there's a minus there. So it will be a negative again. I have a 2/3 here. Oh, I forgot this. This will be canceled there. And then what? Then this gets multiplied by 1/2. So I'll have a 1/6 here. Is that correct? 1/3, and then there would be a 1/2 outside, so that's going to be a 1/6. And then I have x to the 1/2 here and x to the 3/2 here. So there would be an x left on top, and then sine root x dx. Okay. Hopefully I didn't mess up some of the calculations. Can you confirm if this is correct? I hope you were not lost in the process. It's a lot of algebraic manipulations, but I hope we did it right. Okay. Let me just browse above. Okay. Now, I don't think I'm getting anywhere. uh-huh. Let me see. Did I botch the choice of U and DV here? Sine root X. Can you guys check if I did something wrong while I look at the rest of my solution? I hope I didn't do anything wrong in the substitution and in the arithmetic. I guess I did something wrong. Hold on again. Yeah. Yeah. And you see why I don't think I'll get somewhere here? Because this integral. My choice would have been to let u to be to take u to be x to be, or actually I don't have a choice, but to choose to take u to be equal to sine root x, and then dv is equal to x dx. But again, I will just be increasing the powers of x in here, so those x's will never be gone in my solution. So I guess this approach for the IBP won't work here. That's why I'm thinking of another trick. So here, I guess just IBP. If I did all the calculations correctly, and I guess Maria also confirms that, um, IBP is not, or this IBP, this particular solution, is not getting us closer to the solution. And that's what happens when we do the classes or the examples live. But let me see if we can use this trick. I'm thinking probably I can use this trick. Perhaps I can write it as root x sine of root x over root x dx. And can I do this? Yeah, you mean, yeah, I'm actually Hersen. I'm planning to do question 10 after. I didn't expect problem 20 to be this complicated. But anyway, this is what another approach that I'll try to use. Um, Again, the complication is I cannot use, if you go back to isolate, oops, okay. Usually when you have an algebraic and a trigonometric function, the trigonometric functions is a nice choice for you, right? Because we can differentiate, uh, we can integrate it over and over again. But you see, when we do that, it doesn't seem to take us closer to the solution. So another trick here is to introduce a root x on top and a root x in the bottom, so that I can probably take this algebraic function as my u and this trigonometric function as my dv, in order for isolate to hold. Because remember, uh, we discounted isolate from our solution above. So here I will take u to be root x, and then dv to be sine root x over root x dx. Okay. Then if I do so, du will be 1 over 2 root x. And then v would be, now here I can do u substitution in order to find v. I can let u to be root x, and then I'll have a sine u. There's a 1/2 outside. So basically, if you do the integral here, you'll get, guess you'll get 2 cosine root x. And perhaps there's a negative sign here. Okay, now let's try this one. So the original integral sine of root x dx is equal to uv. So that's going to be uv. So that's going to be negative 2 root x cosine root x minus the integral of v du. So we'll have negative 2 cosine root x times du, which is 1 over 2 root x dx. I forgot the dx here. And this is negative 2 root x cosine root x plus integral of cosine root x over root x dx, right? And then now on this part, I can do u substitution. So here I can let, I can let u to be equal to root x, then du will be 1 over 2 root x dx. So this guy will be negative 2 root x cosine root x plus integral of, well, we'll have 2 cosine u du, which essentially is negative 2 root x cosine root x plus 2 sine u plus arbitrary constant c. And then we'll go back to our original variable, 2 sine root x plus c. And there we go. That's the integral, which is much shorter than the solution I attempted earlier, because I didn't recognize, I just recognized late in the game that using IBP repetitively will just make the integral of VDU much more complicated than the original one. So again, here I used a common trick. I wrote the original integral in this seemingly more complicated form, but this more complicated form turns out to be more apt for an application of the IBP. Okay. All right, I know that's long and probably confusing because of the first attempt that we did, but at least here you see a case where you should recognize that IBP will not take you closer to the solution and you need to look for another approach. Okay. I think Michael sent a couple of questions here. Okay, so let me do Michael's question. He's asking for the integral of x cubed sine of 8x squared dx. Again, here probably you will do, you can, well, I suggest here you do the u substitution first, but will that be fine? I'm looking for the quicker solution here. One for du's will be gone. Okay, probably that's better. Usually we can use IBP in conjunction with u substitution. So for instance here, I will let w first to be equal to 8x squared, so that the argument of sine or the function inside sine will look simpler. So I will let w be equal to 8x squared. Then that means dw would be 16x dx. So what I'll do here is to borrow the x dx. So I'll have x squared sine of 8x squared. I'll borrow one of the x's to come with the dx, because from here I know that dw over 16 would be equal to x dx. All right. So if I do the substitution, so I'll have a sine w here, which looks a little bit simpler than before. And then here, and then here I can have dw would be, okay, x dx is dw over 16. And then we have an x squared extra here, but if you look back at our u substitution, we see there that x squared can be replaced by w over 8. So here I'll have a w over 8 in front. Good. And I think, Michael, that's equivalent to what I'm doing. I just did the u substitution first. I disguised 8x squared so that I don't need to take I don't need to worry about the arbitrary the constants that come with that x squared inside the sign. But you can also do what you said, but that would be, I guess, a little bit more complicated, but we'll get to the same answers. So here we'll have 8 times 16, I think that's a 128. Integral of w sine w dw, right? And then here I can use integration by parts. So I'll take u to be equal to w and dv to be equal to sine w dw. And then du then will be equal to dw. And then v is just the integral of sine w, which is negative cosine of w, right? Good. So this would be 128 times uv. So that's negative w cosine w minus integral of v du. Okay. So this is 1 over 128 negative w cosine w plus integral of cosine w dw. But this is negative w cosine w plus sine w plus the arbitrary constant over there. And then I'll go back to the original variable. So I'll have negative, what is w again? W is 8x squared. 8x squared cosine of 8x squared plus sine of 8x squared plus the arbitrary constant c. All right. And again, Michael, if you move one of the x's to be part of the sine function, then that's perfectly fine, but you'll do the similar u substitution over there. Okay. Is that good? Okay, and then as Herson suggested, let's take a look at question 10, though I might take 2 minutes more than our time today. But let's see, problem 10. It's integral of e to the x sine x dx. And I guess here it's another form of the IBP which will require us to take note that we will go back sometime to the original integral, right? And you'll see later. So remember isolate. So we have an exponential, we have a trig. Trig comes before exponential. So we take q to be the trig function, sine x, and then let's take dv to be the exponential, e to the x dx. And then we compute for du, we'll have cosine x dx, and v is e to the x. So basically this integral here, or let me just write that as this. Okay, it's going to be uv, so that's e to the x sine x minus integral of v du e to the x cosine x dx, right? And look at the integral here. It calls for another application of IBP. So again, I'll take u to be the trigonometric, which is cosine x this time, and dv is still the exponential. Then du is negative sine x dx, and v will be e to the x. So now e to the x, or the integral of e to the x sine x dx, will be e to the x sine x minus, I'll use a big set of grouping symbol here, the new uv, e to the x cosine x, minus integral of v du e to the x minus negative sine x dx and grouping symbol. And then let's simplify it first. Then I'll have a plus e to the x. Okay, hold on. I have a negative here. I have a negative there, so that becomes positive, but there's a negative right outside. So it's still a negative here. E to the x sine x dx. But notice that the integral that we have here is exactly the same as the original integral. If that's the case, when you encounter some time in your IBP, the original integral again, then that means you can stop the process and simply transfer it to the other side. Okay, because we're working with an equation here, we're solving for the integral of e to the x sine x dx. So, and then I saw that again on the right-hand side. So I can add both sides, add to both sides the integral of e to the x sine x. So that will have 2 of e to the 2 times the integral of e to the x sine x dx over here equals e to the x sine x minus e to the x cosine x over here. And then since we're solving for the integral of e to the x sine x, I'll simply divide both sides by 2 to get this. But let's put the arbitrary constant c at the end. All right. So this is what you do whenever you encounter again the original integral in your in one of your IBPs. So if that happens, you need to transfer that term with all the constants that come with it into the left-hand side. So I got the 2 e to the x sine x dx here. And remember, we're looking for that particular integral. So all we need to do is to divide both sides by 2 to get rid of that constant there, and then put an arbitrary constant c. All right. So I guess that's all the time we have today, and I feel that you might have you might need some practice with IBP because there's just a few of you participating in the chat. So what I suggest is try to answer some of the exercises in the worksheet, and then let me know on Wednesday what do you think should we try in the lecture, right? But at least now we saw an example for each. A simple IBP, a repetitive IBP, which is sometimes easier if summarized into a table. Then we saw an example where an IBP is not getting us anywhere near the solution, so we need to look for another approach. And then this particular problem that we solved, or actually Michael's question, is an example of an IBP which is used in concert with U substitution. And then the last one is an IBP where in one part of the solution, we encounter the original integral again. So, but I guess we have exhausted all the cases for IBP. So next time we can basically look at some examples. Yeah, that's why I felt this this lab session is a bit heavy. So if you find it too fast, then you can go back to the recording. And actually, I guess the better way to understand this is to get your hands dirty, try as many problems as you can, and then let me know on Wednesday what caused the difficulty. And another complication here is that section 8 comprised of a lot more, or actually there would be 2 or 3 more techniques of integration. And oftentimes you need to distinguish when is a particular method appropriate or more convenient than the other methods. So I hope by Wednesday we can at least be more more comfortable with IBP before we go to the other techniques of integration. All right, everybody. So sorry, it is we're 5 minutes over time, but okay, let's see each other again on Wednesday, hopefully with your questions. All right. Bye, everyone.